we start? No, yeah. I can start? Are you waiting for more student or no? You ready? Okay. All right. All right. All right. So let's today another 1 hour of tutorial about some solving problems. What I'm going to do, I'm going to explain few problems today, and then I will give you a problem for you to solve, and then we'll discuss the result. And then if you have time, then I'll ask you to come up with a design of, give you a scenario, and you make a group discussion, and then come to address, one of the person in a group can address to solve the problem, okay? So let's go individually first, and then if you have time, we can do group problem solving. All right, the first problem is when you have an anaerobic process design, you want to design how much organic volumetric loading you want to put into the bioreactor. How many kilogram of COD per cubic meter per day you want to put into that. How do you calculate that? Okay, because that organic loading rate, OLR, or volumetric organic loading rate, that is simply given by this formula, right? So each one is expressed what it is. So usually the volumetric loading is kilogram COD per cubic meter per day is the unit. So you need to know three things if you want to know how much the loading of carbon you're putting in the system. You need to know the COD of your waste. What is the carbon in your in the input? Okay, and then you need to know the flow rate, how the volume of the water that you want to pump into that bioreactor in terms of cubic meter per day. How much water going to go in for treatment, and then you need to know the entire bioreactor volume, the volume of the bioreactor. Those are the three things you need to know. Okay, if you know that, then we can figure out how much loading rate to put it in. Okay, so simply put, if you know those parameters, you can measure the upfront how much loading volume organic loading rate you can put in. Okay, so how do you select? You need to conduct some pilot scale studies, find out removal efficiency of your system, how much your bacteria can take in your anaerobic digester. If you are starting a new digester, the bacteria cannot take high loading rate, okay? It has to adjust, right? It has to reach the steady state before it can take the high volume of organic loading. Okay, so you do some small scale study first, how much the bacteria can take, and then you do that. Okay. As a first problem, I will come back to that. I will ask you to solve the problem. The second one is designing based on hydraulic loading rate. How much hydraulic loading rate your water going to, how long it's going to spend inside the reactor. Okay. For that, you need to know these parameters. You need to know reactor height in meters, allowable hydraulic retention time, how many hours the water going to spend, and wastewater flow rate, and surface area of the reactor by meter square. So if you want to know how much volume of your reactor, you need to plug in these equations. You need to know this, you need to know the Q, and you can figure it out how big your reactor you want to construct. You want to construct 10 cubic meter, 15 cubic meter, you can design that. If you want to know surface area of the reactor, then you need to plug in this equation right here. I'll give you a surface area. Okay? So you need to know these parameters first, your height of the reactor, your wastewater flow rate, allowable hydraulic retention time, then you can calculate your design of the volume of the reactor and design of surface area of the reactor. Okay, so this is the basic formula. So I need to come up with these parameters by doing some experiment. Okay, so let's move on to the next question. So how do you find out the solid or sludge retention time? How long the bacteria should stay inside before it can be washed out? So an anaerobic digester is completely mixed reactor will have equal HRT and SRT. When you mix the system, always HRT and SRT are equal. Time is equal. Okay. But if you don't mix it, it goes through plug flow mode from filter and stuff. You keep your sludge as long as possible. So HRT days equal volume divided by flow rate. Okay? So volume is given by this unit, cubic meter per day. Cancel. All you need is divide the volume and divide by the flow rate. You will get the hydraulic retention time in days. Okay? Very simple. That's the formula you need. Okay? For a given SRT and HRT, the size of the reactor can be easily determined. The digester volume equals flow rate time sludge retention time. Okay? So these are the formula you can have to find out when you have a reactor design how much volume of the reactor you need to have, how much loading rate you can put in, how much HRT, how many days of HRT, how many days of SRT. So these are some basic formula you should have. Sometimes people don't use COD as a loading rate. They use volatile solids as their loading rate. So you do solid analysis and you can input your solid data into the system. So if you want to know volatile solid loading rate, that is kilogram volatile solids per cubic meter per day equals how much volatile solid is in your influent, that is the waste that you are treating. You need to do the analysis of volatile solid in your waste and divide that by reactor volume. That will give you your loading rate of volatile solid that you can put in your system. So you need to do the analysis first in your waste, how much volatile solid is in your waste, and you should know the volume of the reactor. You divide that will give you the loading rate. Okay? So for a given volatile solid loading rate, the size of the reactor can be easily determined since influent volatile solid is known to us because you do analysis, you know how much volatile solid is there. So digester volume equals influent volatile solid divided by the volatile solids loading rate. Okay? So it goes both ways. Okay, if you know these parameters, you can calculate the volume. If you know only these parameters, you can calculate the volatile solid loading rate. So you need to do some analysis in your feedstock. What's your COD? What's your solid content? Then you can figure out the parameter of organic loading, HRT, SRT, your loading based on volatile solids. Okay? So with this information, you should be able to design operation of a bioreactor. Okay? So yesterday we did some calculation. I went through a couple of problem set. Today I'm going to give you a problem. We're going to use the same model as like yesterday. I want you to solve the problem individually. Okay? And then later we'll do the group project. Okay? So this is the problem. So I want you to calculate the organic loading rate for the following scenario. Okay? So what you have here, wastewater concentration of COD is 7,000 milligram. The wastewater flow rate is 3 cubic meter per day. Your bioreactor volume is 10 cubic meter per day. Very simple math, right? You need to plug in this equation. You will calculate your loading rate in your system, right? So I want you these are the parameters I'm giving to you. Your concentration of your COD in your waste, how much flow rate goes into the system, the volume of the bioreactor, which are these parameters right there. Right? Simple thing, take your phone and plug in this, that it can give you your volatile organic loading rate. Give you 5 minutes to do that. Right? You guys are with me? If you're lost, raise the hand, I can answer. Okay? You're lost? Yeah? Yeah, I want you to calculate this volumetric organic loading, right? How much COD is going to go into your bioreactor? Okay. Huh? 7,000 milligram is the concentration of COD in your waste. Okay. I want you to go to volumetric organic. Go back to the first slide. Can you go back to the first slide? Yeah. I want you to, one more slide. I want you to calculate your loading rate COD per cubic meter per day. All right? I'm giving you the concentration of COD 7,000. I want you to calculate this with those three parameters I gave you. Somebody already answered that. See? Exactly. That's how you calculate them. It's simple. If you know the concentration of your COD in your waste stream, if you know your flow rate, if you know your reactor size, you can calculate how much organic loading you want to feed them. So that means if your 7,000 milligram COD in there, you need to adjust, calculate the loading rate for the calculation that we made. That's how much it should go per day into your bioreactor. Okay. Anybody has any doubt? And anybody in the Zoom there have any questions? Everybody's okay in the Zoom? Got it? Okay. All right, let's move on to the next problem set. So in order to know this, you need to do analysis. You need to know what is in your waste. You do COD analysis, you need solid analysis if you do solid loading rate. You cannot just figure it out. You need to know those parameters. If you know the parameters, you can calculate it. Okay? Okay, next we'll go to the next question. I'll move it here if I want me to move. Then you need to move it first. All right, let's, the next problem. This is exactly like yesterday. I want you guys to calculate it. You take out your calculator or phone, okay? So here, I'm asking you how much methane gas can be generated through complete anaerobic degradation of 8 kilogram of COD at standard temperature and pressure. Okay, that's a question. If you want to take a screenshot, take a screenshot. All I want you guys to figure out how much methane gas you can generate through complete anaerobic degradation of 8 kilogram of COD at STP. Okay. So there are 3 steps to it. We went through yesterday. I'm going to put that step back so you can follow the step 1, step 2, step 3 and give me the answer. Okay? Okay. Everybody got the screenshot? And the Zoom people took the screenshot, ask them, and then you can go to the tutorial 1 for me. Okay. And then they must actually take the screenshot, okay, of the problem. So take the screenshot of the problem. Okay, now we go to the tutorial 1, then people can do step 1, step 2, step 3, what we went through yesterday. Okay. Yeah, we'll try to go to tutorial 1. It should be. Okay, make it whole screen. All right. All you need to do, I don't want you to simply multiply by the answer here. I want you to go step by step. Okay? All right. Step one, do this step one process. You're going to calculate COD equivalents of CH4, which should be the same. Okay? And then we can do step two. So we already know there's 16 mole in methane, 32 mole per oxygen, 2 oxygen, 64 mole. Then you calculate 1 gram of methane equals 4 gram of COD. Yeah, that's exactly the same. If you want to write it down for your problem solving. So click, I will click it second step. Second step. Yeah. Second step, now you're going to convert methane mass to equivalent volume, and then you can look for that. Second step. So your problem has 8 grams, okay? So you need to calculate for 8 grams, okay, of COD, okay? So that's your conversion of CH4 mass to equivalent volume, okay? And the last one, step 3. All right, step 3. Now this is where you plug in your 8 gram to figure this out, okay? So CO2 generation rate per unit of CO2 removed from equation 1 and 2, we have that. And so any answer, anybody so far? Heard that? 2.8. Yeah, 2.8 is your anaerobic of 1 kilogram COD, and 8 kilogram COD produces 2.8, yeah? Anybody disagree with that number? It's simple, right? Hey, that's how you do step 1, step 2, step 3 to solve problem. Okay? I'm just giving you a tutorial how to do that, okay? Let's give a few more time. Zoom people have any questions? All right, let's go to the next problem. Yeah, in this problem it's exactly like yesterday, but here I changed the number. So you can take a screenshot of this problem. Anaerobic filter reactor has been employed to treat chicken processing wastewater at 20 degree. The flow rate is 4 cubic meter per day with a mean soluble COD of 10,000 milligrams. I'll change the parameters here. Calculate the maximum methane generation rate per cubic meter per day. What would the biogas generation rate at 80% COD removal? I put now 20% goes to biomass production. More bacteria is produced. And then if there is sulfate in it, 3 gram of sulfate in it, what should be your methane, right? So everybody took a screenshot, then we go back to tutorial 1 and you follow the step. Yeah. You can click the next one. Step by step they can do. Next one. Yeah. So go now compute your data points to this. Right? Yeah, 7,000 should go, 10,000 is what now? Right? Figure out the calculation now for this one. So if you compute your data, you should get the number for this, okay, and then maximum generation rate for the data for the problem that you're working on, okay. And then we're going to go to the, if people need some time, we can click it further. Yeah. Oh, yeah. Yeah. Oh, yeah. Let me see. Yeah. Thanks. All right. If everybody caught up with this, then go to the next slide. Yeah. Now go to follow this step. Okay, next, move to the next slide to finish the problem there. So now you can follow these steps. I'll give you 20 degrees centigrade, how much your gas generation should be, and then you can account for sulfate later, okay? Okay, if people are following this, now can go to the last slide that for the accounting of sulfate reduction, and then how much methane for that. figured it out yet? Oh, what's your number? With or without sulfate? With sulfate, what is without sulfate? 9.5 without sulfate, right? What's with sulfate? You need it, okay. Work on it, work on it. So we got that. Reduce the COD concentration if there is sulfate. They're competing with methane production. The Zoom people are okay? And hands are raising up. So far it's good? Good. You guys are doing well at the end of the day. Late day, evening, you're still busy calculating math. That's good. Okay, what's the result? In the presence of sulfate, what's the number anybody come up with? With sulfate? Without sulfate? You calculate with sulfate first. You should calculate without sulfate first. Okay. Everybody agree? Okay. Okay. Yeah, that's close. Yeah, it should be less. When the sulfate is there, your methane production is less. Okay, because your COD for methane is less, right? Okay. So that's how you solve the problem, and I'll give you a few more minutes you to complete, and then we'll have one group exercise as a class. Okay, I'll get you a problem for that. Okay. Okay, so the next 30 minutes, what we are going to do, this format example will be given to you, so you can keep it. So use the same models, okay? If you want a future calculation, so everything will be given to you, okay? The next problem set is, I'm going to give you two scenarios. I'm going to divide the class into two. The Zoom people have to, they have to do on their own individually, okay? They can choose either or problem in the Zoom, okay? So let's equally divide this class into two groups. I want you to discuss among yourself, and then you're going to come in front, one spokesperson per group going to present the result. You have to come to a consensus, okay, in your discussion. I'll give you 30 minutes to do this, okay? So the first problem is you got to create biorefinery concept for sugarcane production of 4 tons per acre sugarcane production. The total acreage is 10,000 acres. You can calculate how much. Yeah. First problem set is your production yield is 4 tons per acre of sugar cane. Okay. There are 10,000 acres in cultivation. I want you guys to create a biorefinery concept. That means you wanted to show how you're going to use the sugar cane and produce various product out of it. I'm going to put that slide back so you can look at that. The various products are sugar, ethanol, vinasse, bagasse, all that thing, CO2, okay? So you're going to discuss among yourself that one group, okay? Hopefully Zoom people get that problem. The second group, you're going to, with cassava, which is what we call here tapioca. Okay, tapioca yield is 2 tons per acre, and it's 20,000 acre cultivation. Okay, I want you guys to create a biorefinery concept. Okay, so let me give you guys 25 minutes to figure out as a group, and then 5 minutes to come, and each group will give a presentation. Right? Zoom people got that? The simple problem is sugarcane is 4 tons per acre, 10,000 acre cultivation area. The cassava is 2 tons, 20,000 acres. Okay? Let's go back to the biorefinery slide from this morning. So this is the time to divide yourself. Talk yourself which group, group 1, group 2. This is where you got to talk. It's not silo, right? I want you to participate. So mingle and make a group. I want a group 1 and group 2. I'll give you group 1 people, sugarcane. Group 2 people is cassava or tapioca. Okay? So I want you to go to the slide that says sugarcane. No, the yield we show you. Where is the sugarcane yield? So this is from sugarcane. The PPT, yeah. You go previous slide. Go previous slide. Go previous one. Where's the sugarcane? Go all the way. Yeah. The one says what are the different products you're getting? No. Go. Oh yeah. Yeah, this one right there. Yeah. Make that bigger. Okay. So you guys have to model this. Okay. So you're going to get your juice, get your vinasse, get your ethanol, and bagasse, right? So I want you to use the same model for tapioca as well. Okay. Same parameters. Okay. Yeah. So you need to calculate the 4 ton times 10,000 acres, 4 ton versus 20,000 acres, and come up with the yield and for production. And then I want you to say how you're going to design the concept of biorefinery. Okay. So you're producing multiple products, right? You're producing ethanol, you're producing carbon dioxide, vinasse, and producing bagasse. Those are the products you're producing from here. Okay. And let's go to the next slide. There's going to be more yield in there. Go to the next one. Go next one. Next one. Next one. Yeah. So here's a little more clear. Okay. So you can see the numbers here. That means if it is 2 tons, it will be half of it. 4 tons will be this, production. And so calculate this for both crops. Okay. Time starts now. At 5 o'clock, one of you from the group going to discuss. Okay. And the Zoom people figure this out, and I can't help you out. I don't know how to do it through Zoom. So choose a problem, try to come up with a biorefinery concept, please. Okay. You're not talking. Group, make a round table. I want you guys to talk. Make a discussion. Make. This is sugarcane, this is cassava, right? All right. I want you guys to group, talk, discuss, come up with a strategy, and how you're going to do your biorefinery. Huh? The first slide is the same slide. This is the yield. You want the first slide or this slide? It's the same thing. But this has a number in it. See there's a number? It says how much juice you're going to make, how much sucrose you're going to make, how much carbon dioxide you're going to make, how much vinasse you're going to make. Okay? if you're making cassava feedstock, when you make ethanol, you still make vinasse, okay? So, but your rate is you're making 2 tons versus 4 ton. Your acreage is 20,000. Your acreage is 10,000. You see how much sugar going to come when you have all the acres are cultivated. Figure out the numbers, and then I want you to say what are the product you will make, right? And then put a rough dollar value and come up with whether you're going to make profit or not. Okay. I hope they are working out. I don't know. That's a problem. Yeah. They follow this example. But if they're working on sugarcane, it's 4 tons per acre, 10,000 acres. If they're working on cassava, 2 tons per acre, 20,000 acres. Makes sense. dioxide going to sell $5 per kilogram. Okay, okay. Carbon dioxide rate is $5 per kilogram, and ethanol production, ethanol going to sell for $2 per liter. Okay, and then you have bagasse. It's going to sell for 2 cents. 2 cents per kilogram. Okay. Yeah. So vinasse goes for $1 per liter. Okay. Right. So let's calculate the amount, and then I want in 5 minutes one of you in each group going to discuss. Everybody going to share. All right. All right.
So the problem which was given to us was the sugarcane biorefinery. Actually, we tried to figure out many things. We tried to figure out from a 1 metric ton as the plot is saying mass balance. We tried to figure out the cost. Actually, it comes out to $40,808.
Okay.
And we try to provide this. We tried to close the loop around. We tried bagasse for thermochemical conversion, ethanol for blending, and then this vinase for anaerobic digestions, and then digest it to this organic fertilizers, and then the CO2 for algae cultivation, and from the water from the whatever the wastewater we use for algae cultivation, and then we try to purge CO2 in that as a algae source for algae, and
So you completely close the loop.
we try to close
the.
so we tried to close the loop. But
Okay.
biogas and
So you took the CO2 instead of selling the CO2, you put it in the algae cultivation. Excellent. You went more than what I thought.
yes, sir. And bagasse also we try to utilize as a pyrolysis or gasification for electricity generation. Yes.
Okay. So you put everything in.
Yes, sir.
Everything to the
Yes, sir.
problem solved.
Yes.
Is it a good idea? Do you think it's going to workable? I know you put them, whatever you learn into the problem.
Yes, sir.
Yeah. That's another question, right? Is it doable?
Yes. Ultimately, it becomes the economics of a scale, sir. If some entrepreneur took up, he will definitely see his money only.
Yeah.
If it is going to be benefited, then only he will put his money.
Exactly.
Yes.
I mean, if the investor is investing into this,
Yes, sir.
all he looks for is dollar sign, profit.
Yes, sir.
How much I'm going to make money, right?
And then
You
sir,
can give all the ideas you want. I want to close the loop. I want to carbon neutral.
Yes.
He doesn't care. You got to convince them.
And then, sir, we also
Yeah.
wanted to when payback period and all those things.
That's right.
To be
Return
but
the-
the return period and then yes.
Yeah, exactly. But academically, excellent idea. What you guys did was close the loop. Carbon cycle was complete. Okay. Excellent. Excellent. Good, good. All right. Let's talk the second group. What you guys come up with? You can sit and talk. You don't understand up. Okay.
Thank you, sir. So our topic was the biorefinery of cassava waste.
Yeah.
I mean cassava. So what we have planned was just a flow chart,
Okay.
and we haven't done any calculations yet, sir.
Yeah.
So what we are planning was after the cultivation of cassava tuber,
Yeah.
it will be segregated as starch and then peel. So to maintain the zero waste, we will be transforming that peel into a char.
Okay.
And it can be used for absorption purposes
So
for
you,
other.
you're gonna make a biochar.
Yes, sir, for biochar, and it can be used for other absorption purposes.
Yeah.
And the starch will be gone through washing, and it will be producing the pure starch and the waste residue and the water washed waste also.
Okay.
So we will be segregating this as three steps. The pure starch will be gone for the food industry for sago production, and the residue will be gone for other next treatments, and the washing starch washed water will be gone for biogas production directly, as it contains some sugar and gone through fermentation for the production of biogas, from which the gases collected based on the composition can be segregated and used for other purposes also. And the waste residue produced from the starch washing can be will be subjected to pre-treatment processes, as they contain complex polysaccharides. So they will be converted into simple sugars, and those sugars will be used for the fermentation process for the production of either volatile fatty acids or ethanol or other acids, then methane production, and if required we can divert it to biohydrogen production also. Based on the pathways and the organisms involved, we will be following these processes, and along with this some byproducts will be produced. So those byproducts will be used for other based on the byproducts produced. If the acetate or acetic acid is produced, other acids like carbon dioxide will be used for beverages, etc. And if hydrogen is produced, it will be along with a little amount of acetic acid, so it will be used for acetic acid based products. If volatile fatty acids are produced, it will be along with a little amount of hydrogen and carbon dioxide, so it will be diverted to the sources of usage. And then the last, the
It all will be produced. You say if it will be produced. It will be produced. If, not if, it will be produced. Okay. Okay.
if the pathway changes, so it will not follow the pathway and other products might be produced. So
If you want to stop, you can stop it. What product you want, you can do that. Yeah, yeah, yeah.
so, and at the last, the digestate will be produced. It will be subjected for the biofertilizer usage. So we are planning for a zero waste management.
Exactly like the group. So what is the main product? Starch? What is your profitable making product in your...
It's starch, sir.
Okay.
So the main product will be the starch, which will be used for the sago production in the food industry, and the other byproducts or waste products from that processes will be used for other for other
So
usages.
you're producing ethanol,
Yes, sir.
anaerobic digestion,
Yes, sir.
put everything into that calculations.
Yes, sir.
Right?
This can be done in a particular industry in the whole process if this industry is taking up this idea.
Right. I think excellent. I mean, both group are trying to close the loop and try to produce as many product as possible. Right? They're producing. I didn't think about you guys doing torrefaction and biochar, which is something you guys think out of the box, and I didn't expect that. Yeah, yeah.
So it only becomes the question who will get the investors first.
Is it-
That is depends on what way you are projecting your proposal is very important.
Yeah.
Investor doesn't matter. It's what way you are justified your
Yeah, how you are selling it? Yeah, yeah.
Nowadays, you see the government of India is giving lot of sponsor for the startup. Okay, if we have the process, just if you approach them, then immediately they are ready to fund nearly 25 lakhs.
Yeah, you have to sell it to the people that invest in. Okay.
They are asking that some model.
Yeah.
Show it, so immediately they are funding.
Wonderful. I'm
That DST startup
nice. I'm really happy. The guys are really actively participating. I was even though it's a very late evening, I'm really happy that you guys are very, very engaged. Okay. All right. Thank you. I'll have a good evening. Good. Thank you. Thank you.
This will stop it.
Yeah. Wait.
Okay, thank you all. This tomorrow morning 9:30 we have these sessions. Okay, so all of you join tomorrow morning at 9:30. Okay, thank you.